Recording in progress.
Yeah, let's start off. Hope everyone has gone through the ASICA thing, but in case you have not gone through it, make sure to do it in the next 2 days, right? Maybe today we will not be doing that much of an AC. Maybe we'll focus more on EMI today. But it's important you go through it because AC, once you got that phasers ka thing, it's pretty easy. Like when we can see 4 or 5 models and you'll be able to handle everything. So let's go ahead. You got a capacitor, we got a resistor, we got a battery here. This is grounded. We have an inductor, resistor, battery. Yeah, perfect. This is A, this is B. In this branch, the current is 0. This thing, 2-volt. Current in this branch is I is equal to T. This resistance is 5 ohms. This inductance is L is equal to 2. This thing is 5 volt. This thing is 1 ohm. This thing is 2 ohms. Let's make it 3. So on this capacitor, on this plate, we have charge Q is equal to T square by 2. This is point C, and this capacitance is 2 farad. Did I not give anything here? Battery, resistor, capacitor, inductor, every damn thing is there. Find the voltage at ABC at T is equal to 2 seconds. So this is A, this is B, this is C. Find the voltage at A, B, and C at T is equal to 2 seconds. Let's get this thing. Hope everyone remembers the sign convention. So how do we go about it? So that thing is grounded, right? So let's go towards. So this is 0, that is 2 volt. So this point ka voltage will be 2 volt. Make sense? Because this is 0, this is a battery, that point should be 2 volts. So let's go from, let's try to find the currents, okay? In this branch, current I is equal to T. What is the current in this branch? The current in this branch, if I call it I dash is nothing but dq by dt, which is also T. Right? So perfect. I could have given something else, but okay. I is equal to T. So at T is equal to 2 seconds, meaning this current also will be 2 ampere. This current is also 2 ampere. This branch may current is 0. So this branch may current must be 0 because whatever is coming, everything is going. Junction law is valid. So there is no current in the branch A. Clear with that? So first get all the currents. And then apply Kirchhoff's law. We can start from A. I'll go from VA. I'm going through the battery, 5 volt. There is no current there. So that is 0 into 1 ohm. And then I reach 2 volt. So VA is equal to minus 3. Go from B, VB minus 2 ampere into 5. Then LDI by dt. So LDI by dt. And then I reach 2 volt. L is 2 and di by dt is 1. So that will be minus 10, minus 2, minus 12. So VB is equal to 14. Make sense? Then go from C, VC, you're going from negative to positive plate. Remember, if that is plus Q, then this is minus Q. So that will be plus Q by C. You're going opposite to the current. So plus I dash into 3 is equal to 2 volt. So at T is equal to 2 seconds, charge will be 2 coulombs. So VC plus 2 by 2 plus I dash is 2 into 3, 6 is equal to 2. So that would be 7 minus 5. Clear with this? Any doubts on this? Check it out. So you can get as a function of time t and then you can substitute, or you can already substitute. Again, not a tough one, but you should know how to use Kirchhoff's law and everything for the elements and stuff. The sign convention and everything. So just be careful with that. So junction law, inductor, capacitor, resistor, everything is there. Any doubts on this? Clear? These are some standard ones. So we have an inductor. N is the number of turns per unit length. So we have a current I is equal to T. And now what you're doing, you have actually introduced a rod. The relative permeability is mu R. This is there in the class notes. Permittivity. It has gone X inside, and this thing is moving with a speed V. Find the back EMF as function of time t, or t is equal to 1 second. Find the EMF or the voltage across inductor at time t. T is equal to 0, X is 0. So you're introducing a metallic rod into the inductor. It is continuously entering there. The length is L, radius is R. N is the number of turns per unit length, tightly wound. Find the back EMF across this thing. So all these are concepts. I'm not saying they'll get the same question, but the idea is important. So what was the catch? These are basically two inductors in series, L minus X. You can treat them as one inductor and one inductor. So this L1 will be, remember the formula, mu naught n square pi r square L. This will be L minus X. This is L2 will be mu medium, which is mu relative into mu naught n square pi r square X. That is the self-inductance of a solenoid, mu naught n square pi r square L. So you should know your results. So L equivalent will be, add them up, L1 plus L2. Mu naught n square pi r square L minus X plus mu relative into X. That's your self-inductance as function of X. X is equal to Vt. Now, the important thing here is flux is equal to Li, and back EMF is minus d phi by dt. So you have to be careful, because generally the habit is what? Remember writing as LdI by dt. But here L is also changing. So this will be minus L di by dt. That's it. That is the main concept there. Minus I dl by dt. So if someone asks you what is back EMF, it is d phi by dt. And what is phi? Li. This is like variable mass system. Remember I told you there also. So back EMF is not L di by dt. That is valid only when L is constant. हो गया ना? L तो you know as function of x. di by dt is 1. Current is a t, and dl by dt you can differentiate and get it. So I will leave it to you. You can handle it now. Clear? That's it. Again, not a big deal, but that is the thing. So there are two inductors in series, and then you can figure it out. That's one again concept. It's like variable mass system. We have a variable self-inductance. You cannot say E is equal to L di by dt. That's the main thing. Third one. This also we did in the class notes. So we have a long solenoid. This is infinity, but this is an open end. Now, when you look at the field lines, these are the last field lines to enter this corner. I'll color them in green. See. So lot of lines are entering, but these last green lines are the last ones to enter. So these green lines right here, this will be X. The radius of this whole thing is R. So these are the last field lines to enter the open end of a solenoid. Find X. So we got a solenoid here whose radius is R. This is an open end of a solenoid. So the field lines are entering from the open end and they become parallel when they go to infinity. So technically speaking, now some lines will actually generate in the middle also. I'm not drawing it, but there are lines coming from the middle of the solenoid. So these green lines are the last lines to enter from outside. Yeah, Mehan remembers it. Find X. So these lines, when they become parallel at infinity, they don't occupy the whole space. So they'll occupy only up to radius X. If the initial radius was R, what is X? This is a semi-infinite solenoid. Some of you guys didn't revise the notes. If you had revised, you would have just told the answer. Advait. What was the catch? See, when you take a semi-infinite solenoid, the field lines are entering at different things. But what you will notice, the field here, think about this. If you join two semi-infinite solenoids, it becomes an infinite solenoid. Then the field inside should become mu naught Ni. That means each half solenoid will generate a field of, let's call it Bx. This component will be Bx. This component is Bx. So Bx will be mu naught Ni by 2, not the total field. All the field lines entering from the open end, their horizontal components must be mu naught Ni by 2. Making sense? So when you combine two half solenoids, mu naught Ni by 2, mu naught Ni by 2 will add up and you'll get a full field mu naught Ni. So this thing, right? We did it in magnetism. Solenoid में किया था ये. This was the concept, page 169. The open end of a solenoid will have a field of mu naught Ni by 2. Page 169, magnetism. right? So then what is the flux entering then? Then the flux entering will be B into perpendicular to this thing. So Bx into pi r square. So when these lines come here, and you're saying they're occupying a distance of x. So this flux will be, now what is the field here? At infinity, the field here becomes mu naught ni because you're infinite solenoid here. That will be mu naught ni pi x square. So the flux must be same since the number of lines are same. So mu naught ni pi r square must be equal to mu naught ni pi x square. X is equal to r by root 2. Clear with this? That is the idea there. So the field on the open end is not mu naught ni by 2. The field at the open end, horizontal component is mu naught ni by 2. Clear with this? And the logic is this. If you join two semi-infinite solenoids, it becomes an infinite solenoid and this becomes a midpoint. And the field there should be mu naught ni. So each half must be contributing mu naught ni by 2 in the horizontal direction. Clear? Again, not a tough one, but conceptual. This is voltage versus time graph. So we have a voltage like this. So this is V naught, T by 4, T by 2, 3T by 4, and this is T. And this is minus 2 V naught. Find VRMS of this voltage source. I hope you remember, right? For a sine function, VRMS is V by root 2. For a triangle function, V naught by root 3. So someone made a weird zombie function here. 1/4 is a sine wave. 1/4 is a triangle. 1/4 is a straight line. 1/4 is again a triangle. And this thing just keeps repeating. This is an AC source. The definition of AC is if the current should change direction periodically. There is a periodic function whose signs are changing plus and minus. How do you find RMS for this function? (13 by 24). I don't know. Let's see. People are preparing for mains, I guess. Only 17 people today. And that is there, understandable. Monday we'll have only class, no exam. So I will wrap up by 30 or something. So that second say, na, exam? And we'll start after the mains. Hope everyone applied for UG exam, na? UG exam apply kiya, right? Date kab tha? 19th, right? 17, I don't remember. Anyone remembers what is the date? No, I don't remember. Keep checking that. At least you should know when is your exam ka date. 2nd May. There is an interview and a written exam, right? Okay, 2nd May ko hai kya? Okay. Fine. I think there were 2 dates, I guess. They decided on 2nd May. Maybe I didn't read the update. Not. How do we do this thing? So try to understand the meaning of VRMS. How do you define VRMS? It is a DC voltage which will give you the same amount of heat as the AC source, isn't it? So first of all, we know for this function, the RMS value will be V naught by root 2, meaning you can replace this sine wave with a DC battery of V naught by root 2. For a triangle function, you can replace with peak value by root 3. The straight line is straight line only. This is also 2V naught by root 3. That means now I can create a new function like this. So the sine wave is as good as having a DC battery of V naught by root 2 for how much time? T by 4. Then this battery is similar to having 2V naught by root 3 then this is similar to having a battery of 2 V naught. Then this is similar to having a battery of 2 V naught by 3. You can replace these functions with constant voltage sources. And now you're telling the heat produced in because of this voltage. So you want to replace this with a resistor and a constant DC battery, VRMS. So what is the heat produced? Heat produced will be V naught by root 2 whole square by resistance into time T by 4. So for time T by 4, you can assume the battery is V naught by root 2 and you can just find the heat produced. And 2V naught by root 3 whole square, V square by R is the power T by 4 plus 2V naught whole square by R T by 4 plus 2V naught by root 3 whole square by R T by 4. And now you're telling all this function is equal to VRMS square by R T. Clear with this? T will cancel, R will cancel, VRMS aa jayega. I will leave it to you. Solve and see what you're getting. Got the idea? So for a sine function, triangle function, you know. So you can just put RMS value of that, replace with DC batteries and just get the heat and you're done. That's the trick there. If they give you a combination of these different weird functions there. We got an inductor. We got a rod. Magnetic field, gravity, mass M, length L, inductance L, released from rest. You can take this position as y is equal to 0. So y-axis is this. I'm taking down as y-axis. Find the displacement of the rod as function of time t. Find the current in the inductor as function of time t. I can ask you anything. These are long, okay? So this is never ending, don't worry about it. It's big. So there are 3 cases of this: resistor, capacitor, and inductor. The remaining 2 I'm not doing. Do check it out. Inductor is a good one among that. Resistor, we can see a variation of it. What did you even find actually? Displacement. Why is it equal to something? What did you find, Advait? Displacement is equal to something, right? You got G by omega square. Omega is equal to B square L square by ML. What is that? Minus sign है क्या वो? Okay. So you got omega in terms of omega. 1 minus cos omega t into omega is B square L square by ML. Okay. Hope you guys realize this thing, right? This is an SHM. भाई तो बोल रहा हूँ, the moment you see the question, you should know, अरे this is an SHM, it's a standard model. If you can't figure out that in the exam, you will waste your time thinking what to do for 10 minutes and then you're gone. You see a question within, if it's a standard model, first 10 seconds, you should know what to do. Then it will take 3 to 4 minutes to solve. Then you can finish all the question in 3 minutes, 3 4 minutes max. That way you can handle around 15 to 16 questions in the paper. So how do we start? I can ask you a lot of things. Find the maximum current and everything. So let's say after time t, this velocity is v. If this guy is going with velocity v, it acts like a battery here, BLV, and this will be the current. So we have BLV minus LDI by dt is equal to 0. That's your equation there. And when you write the rod here, we have the force ILB, mg, and acceleration. So this will be mg minus ILB is equal to ma. Right? Differentiate. If I differentiate this will be LB di by dt. This would be m d, that's dy by dt, d square v by dt square. And I already know di by dt, take this guy and dump it here. This will become b square L square, capital L, into v by mass is equal to d square v by dt square. You can clearly see this is your SHM. So v is equal to v naught sine omega t plus alpha, right, where omega is b square L square by ml. Perfect. I need to find v naught. I need to find phi. So think about this motion. So basically, this will be your SHM here. So what are the initial conditions? At t is equal to 0, velocity is equal to 0. So the phase angle will be 0. At t is equal to 0, current is 0. Therefore, acceleration will be equal to g. That means dv by dt, which is v naught omega cos omega t, right? This must be your acceleration. So must be equal to g when time is 0. Therefore, v naught is equal to g by omega. There you got everything. So v is equal to g by omega sine omega t. That's your velocity as function of time t. And integrate this, you'll get the y coordinate. So dy by dt. So basically, you're starting from the extreme position, isn't it? When you're starting from rest, this is an extreme position here. So g by omega square cos omega t. Limits, be careful there. 0 to 1, cos 0 is not 0. You get 1 minus sine cos omega t. That's your y coordinate. Once you got the velocity, you can get the current. You can get anything you want here. So substitute v there, you'll get I, you'll get the current. So basically, this guy is oscillating. So this y is equal to 0. I can even find the amplitude. What is the amplitude here? So this here is your v max, which is g by omega, which is nothing but a omega. Therefore, amplitude is equal to g by omega square. Actually, this is the amplitude. There's no need to do it again. This is the amplitude of the SHL. So they can even ask you, like, what is the maximum distance it will go down? So this is your mean position. So y mean is g by omega square. And this will still go further. This will be the another extreme. Y is equal to 2g by omega square. Have a look at the equations. Just give me a minute. Here this. There, this is a pretty good one because you have SHM, you have inductance, EMI, so all stuff combined. It's a pretty good question. You should guys definitely check it out. So if you put an inductor, it becomes like this. So this thing will not stop. This will just keep oscillating up and down. And you can ask a lot of things there though. Same thing, if you keep a resistor, just get me the equations, will not solve the whole thing. So this is the top view. EMF, resistance R. Top view, we got a rod here. Mass M, length L. There is a magnetic field B. Smooth rails. Find the velocity of the rod as function of time t. So basically we can put a switch here like this. The switch is closed at t is equal to 0. You should be very comfortable with these kind of questions. Let's see. That's it. This much time equations आ जाना चाहिए. Solving can take another minute or so. So the moment you close the switch, current will flow here. This guy will start creating a battery of its own, which is fighting back with this. And we have a force here, ILB, that will drag it forward. That will be your acceleration. So E minus IR minus BLB is equal to 0. ILB is equal to mass into acceleration, which is mdv by dt. You can take this I here, substitute here, and when you do this, you will get something like, 1 minus e power minus t function types. So when you solve this, you'll get something like a into 1 power e power minus bt. So eventually this reaches terminal velocity. You can find the terminal velocity directly. E is equal to b into L into v terminal, isn't it? When reach terminal velocity, both the rod is generating the same EMF as the battery. So current will stop flowing. If the current stops flowing, there's no force on the rod. The velocity becomes constant. So when you reach terminal velocity, acceleration is 0. So you'll get the V terminal directly from one step. So eventually this rod will reach terminal velocity and yeah, you're done. You'll just keep going. Clear? So when you have resistance, it will behave like a viscous force. You know that thing. When you have a capacitor, you get a constant acceleration. You can check out the notes. And when you have an inductor, you get an SHM. So you get three different cases there. You get a constant acceleration with capacitor, SHM with an inductor, and resistor will be like a viscous force. Again, smooth parallel rails. There is a magnetic field B. We got a rod here, mass M1, length L. We got a rod here, mass M2, length L. So this rod was initially at rest. This is the top view. There's no gravity. And someone kicked this rod with speed u. This is your initial speed. Right? So these rods, right, they have some resistance. Or I can just put a resistor there in the circuit. Doesn't matter anyway. So plot V1 and velocity V1, V2 versus time graph approximately. So they'll give you 4 graphs and they'll expect you to choose the right one. So we have two rods parallel to each other, masses M1 and M2, same length. Then you kicked one rod with speed u and you left it. If something happens, the other rod also starts moving. So approximately, how will these two velocities will look like? That I don't know actually. You have to give the answer. You can't tell all this thing to the examiner, right? They don't give a shit. So get the answer, then you think about whatever you want. Because after 2 months, no one bothers about it. Get it? If you're in 11th, you could have done it. Then we could have discussion. Not now. Let's get an answer for now. Again, not a tough one, but theoretical one. These are the kind of things you can expect even in advanced paper. Maybe around 20-25% questions will be like this. Seriously, you guys are taking time. So what happens here? After some time, let the velocities be v1, v2. Which way but? The moment you kick this, so BLV, so you will have a battery like this. So this will try to push the current. The current will go here, the current will come here, right? And this is also going with some velocity v2 now. So ILB will be this way. So this rod also will start going in the same direction. On this rod, the force will be ILB backward, right? And not only that, there is also an attraction between them. If you see, the current is flowing in the opposite direction. So there is also a repulsion. Mu I square, mu I into I by 2 pi d. D is the distance between them. This is changing though. And this would be mu I into 2 pi d into L into L. Do you guys remember that, right? Force between the two rods. So these are all the forces acting on the rod. But did you notice something? Net force is zero. On the entire system, F net is zero. So linear momentum is conserved. ILB will cancel. The force between them is internal. That means eventually both the rods will go with the same velocity. How do I know that? Think about it. As this rod goes with V2, this also will generate an EMF BLV2. So that BLV1 and BLV2 both are fighting, isn't it? So when the current stops acting, when the current stops flowing, force becomes zero. Right? When V1 becomes equal to V2, current becomes zero and velocities become constant. So they kind of behave like perfectly inelastic collision. So the magnetic force is dragging them together. So then you're done. Mu is equal to M1U is equal to M1 plus M2V final. So V final will be M1U by M1 plus M2. So both the rods will eventually reach the same velocity. From there, you can even find the heat produced, isn't it? The change in kinetic energy is the heat produced. Now, if you try to plot the graphs, so this is your V final. So one rod, this guy who is starting with speed u, this will decrease, decrease, decrease. And yeah, this will take a long time though, it'll take infinite time. You will eventually tend to this line. You'll get closer and closer to this line. The other guy starting from zero, that guy will increase, increase, and will tend to this line. Clear with this? Yeah, the different there will be a small difference though, because the masses are different. This will have more acceleration initially. Again, depends on who has more mass. So initially the slopes will be different. Yeah, but this also will get closer and closer to like this. Clear? Both the lines will not have same slope. Because the masses are different, accelerations are different. Clear with this? Yeah, but eventually they'll reach V final. So maybe I can draw it like this. So example, for example, if I say M2 is greater than M1, then your V final will be somewhere here. It will be more down because then this guy will be something like this. something like this. You're getting it? The slopes will be different. Making sense? If M2 is very, very large, what will happen? It will reach V terminal very fast. So they will, but yeah, they will take infinite time to reach. Graphs would look something of this sort. Are you clear with this? If M1 is equal to M2, they look symmetrical. So they can give two graphs looking like this and they'll mess up with the slopes. So yeah, they can play around. So be careful with that fine details because the masses are different. Accelerations will be, F will be same. So F by M1 and A2 is F by M2. So that's one way to play around. And then this would be another good question here. So we have a capacitor. We have a resistor. We have a switch. Capacitance, resistance. You kept a rod here. Mass M, length L, magnetic field. Top view, there's no gravity. Smooth rails. This thing has a charge plus Q and this thing is minus Q. The switch is closed at T is equal to 0. Find the velocity of the rod. I can ask you find the final velocity of the rod. Yeah, I can ask you velocity of the rod as time T. If I don't keep that resistor, it's much faster to do. But let's put a resistor and say this, right? This is a concept of maglev. Ever heard about that? Maglev or there is a name for this thing. Railgun. Ever heard about it? So railgun is simply like, you have a magnetic field and you generate a millions of amperes of current and you send through the rod. Because of that huge current, this force ILB, the rod will accelerate to high velocities and it is projected outside. So you can actually use it like instead of firing a chemical weapon and shooting down, you can actually use this to shoot down things. These things can reach speeds up to 12 kilometers per second. That's more than escape velocity. So far they do have weapons like this. US and all, they did build it, but the problem is this: every time you fire, this thing has so much kinetic energy, the barrel gets destroyed. So you literally have to keep changing the barrel every time you fire. Too expensive. But these things go with such a high velocity. They say like, this projectile will simply pass through a battle tank like a knife on a butter. It just cuts it. Yeah. That is the futuristic weapon. So tomorrow aliens are coming and we have to fight them. Maybe we will put them on moon and then maybe we'll start fighting with aliens. It will be interesting. How do we handle this? So it's like an RC discharging circuit with a rod, isn't it? Let's see. I just kept a resistor for fun. Without resistor, it is easy to do. I think we should get something. So the final velocity will be independent of resistance. That's the catch. Start like this. Let the charge Q come out of the capacitor. You have to integrate. There's no way out. The moment I say time t, there is a catch. So this circuit is closed. So let charge Q flow out from here. So this guy will be Q minus Q. So this will be the current. So this is the current. So this guy is being dragged by ILB. That's your acceleration. But this is also fighting now. This will have a battery BLB. So if you write the equation, you're going from negative to positive plate. So Q minus Q by C minus IR minus BLB is equal to 0. Differentiate. Capital Q is constant. Minus Q, that will be I by C. This will become di by dt. This will become BL acceleration. and this will be ILB is equal to MA. Take A from here and dump it here. So minus I by C minus DI by dt R minus B square L square by M so into Y is equal to 0. That you can integrate, right? So you got DI by I, and then you can put it there. Or anyway, you want to find velocity. So DI by dt is equal to, you can get velocity. You can do it however you want. So you got the integration anyway. I got the current as function of time t with this. So di by I, and then you can bring all dt and that constant here. And then you get I is equal to something. A into, you'll get some value there. You'll get current as a function of time t, right? Once you got the current as function of time t, I can substitute here. I got acceleration as function of time t. Integrate, I'll get velocity as function of time t. Maybe we should do it, I guess. Let's do it. LB di by dt is equal to m d square by dA by dt. Take this, substitute here dA by dt. I think the previous one is only better, I guess. I will leave it to you. We can integrate, that much you understood. So just tell me, I'll tell you what will happen to the final answer. When you solve this, you will get current from here. Once you got the current, you will get acceleration, then you get velocity. Okay? Little work, but you'll get it. Now, how will the final answer look like? How can I get the final velocity without doing all this stuff? So this will be actually a good RC discharging circuit. You will get this I is equal to some I into e power minus some KT types, T by tau. So the tau is your time constant. So you'll get on this form. Okay? Now think about this. Eventually the rod will reach some velocity. So the rod will reach a certain V terminal. At that point, this guy will act like a battery, which is BLV terminal. At infinity, current will become 0. That means the charge on this capacitor, right? The voltage across this and voltage across this must be same. Isn't it? Q by C will be equal to BLV terminal. You're getting what will happen there? So eventually, right? So once you know V terminal there, you can even find the final charge on the capacitor. So the capacitor won't get fully discharged. Only part of the energy will get discharged. Are you clear with this? So once you get V terminal, you can find the final charge on the capacitor. So the capacitor will not get fully discharged. It will not become 0. And you can't conserve energy because there is a resistor sitting there. Limits of the current, 0 to I. Initially, there is no current when you switch it on. Initially, when you switch it on, what will happen? The moment you switch it on, the current initially will be Q by C by R, na? Right? Because there's no velocity, there'll be no EMF here. So this V was 0. So you will get the current value from there. I think if you do like that, na, it is better you find V as a function of time t only. Limits ka problem nahi aayega. Clear with this? You can handle that, right? So current ka limits y hoga. T is equal to 0. The current I will be Q by RC. Okay? So what is the potential difference across the capacitor? Q by C. What is the resistance? R. That's your current. Because initially the rod has no velocity, there'll be no EMF from the rod. Okay? So all the potential difference across the capacitor will go across the resistance at that instant. Clear? So, and then you can find there that way. Clear? So yeah, it's an RC discharging circuit with this, but I would say please integrate this and check it out on your own. Right? You will get it. So the idea here is the final velocity, right? V terminal will be independent of resistance. So that means, you know, what we can do, we can keep a very small resistance. Then the time constant also will be very small. That means the moment you close the switch, the capacitor will discharge in a very short amount of time. and you reach V final in a very small amount of time, isn't it? So you can achieve very high speeds in a small amount of time. So that's what you do in a railgun. You want to fire the bullet, you want them to reach speeds of 10, 15 kilometers per second in a matter of 2 to 3 seconds. Making sense. So by making the time resistance very, very small, you can create time constants of 1 millisecond or 1 microsecond. So this thing will fire off. You should definitely check that out on your own. That's one way to do. But if you want to see the same case without a resistor, how do you think we should do this one without a resistor? There's no integration, nothing. So again, here also what we do now, we do something like this only. We will say end of that equation will look that way only. We will say during that small time instant, there will be some current I here. We don't know how much is the current. So in time dt, capacitor discharges. So we have a force ILB. Okay. The final charge will be Q. This will be minus Q. This will achieve V velocity, V final. So Q by C is equal to BL V final. This is one statement. Second thing, now when this force is acting, integral F dt is equal to change in momentum of the rod. What is F? ILB dt is equal to MV final. I don't know the current, I don't know the time, but I know what is integral IDT. Integral IDT is the charge discharged by the capacitor. How much was that? Initially you had Q, now you have small q, which is Q minus small q is equal to MV final. Take V final from here and substitute. This will be LB Q minus BL V final C is equal to MV final. So this will be QLB by M plus B square L square C is equal to V final. There. You get the same answer for the previous one, independent of resistor. Heat produced will be same. Basically, I made R tending to 0 here. Clear with this? So this is the same question. I just added a resistor. It became a little more complex. But this was a more easier one. So we actually use impulse kind of thing here. When you close the switch, the charge will discharge in such a small time. The rod will feel there's a huge current, and the rod will feel someone kicked it. All clear with this? So that's one good thing. So do check it out. So based on this, let me ask you one more like this. Let's say we have a long solenoid, okay, very long solenoid. N turns, the radius R. This thing is connected to a resistance R0. Let the radius be A. Now what you did, you have kept a square. And in this square, current is equal to some kT. You're getting how is this current going? Now, because this current is going here, it will generate a magnetic field. And that magnetic field will change with time. If the magnetic field changes with time, then there is a flux induced in the solenoid. If there is a flux, it will generate an EMF, and that will give a current in the resistor. Find the current in the resistance. You're getting the question? There's a long solenoid. This thing is from the center, okay? The square loop, long solenoid through the center. The width is also small. A long solenoid. Along the center of the square. The radius A, right, of the solenoid is very small compared to the radius, the side of the square. So this side of the square L is much, much greater than small a. So you can ignore the size of the solenoid in front of the square. Current is equal to KT. Think. This thing you can do without even finding what is the magnetic field due to the square. Don't try to find the magnetic field due to the square. You can do without that. Think. Take 2 minutes. This is some good one. These are the stuff. But did you guys get the idea, na? Why there'll be a current? That I told you. They will not tell you in the exam. You need to figure out that. So that square loop is creating a magnetic field which will pass through the solenoid. And because its current is changing with time, that B also changes. So there's a change in flux. And so there's an EMF. And yeah. It's a long solenoid. So compared to the square, you can think it's an infinite one. Think. Take 2 minutes. Let's see. So the result we get right will be quite interesting. See. So at a distance x, take a small dx. So the flux in that small dx will be the number of turns, which is n into dx. Let's see, Janet. So that will be the number of turns, because n is the number of turns per unit length. Magnetic field B, which I don't know. So this guy will generate some magnetic field here, B. And the area will be pi a square. This is the flux. Now we want to find the total flux. This will be n pi a square integral b dx. Make sense? I don't know b, but what I want is integral b dx. Now what you can do, this is an infinite solenoid. So I will just assume there is a big loop. Let's call this point A, B, C, and D. Okay. And now when you have this loop here, understand only because of this loop, you have a magnetic field B here on this region. Now, if I try to apply Ampere's law, when you see integral B dx, doesn't it look like integral B dot dl? So if you apply the Ampere's law, integral B dot dl on this loop ABCD, shouldn't this be mu naught into I, the current crossing? But remember, this thing is already at infinity. So this guy is at infinity. This is also at infinity. Right? This is also at infinity, and this is also infinity. So this can be written as integral B dl A to B plus integral B dl B to C plus integral B dl C to D plus integral BDL d to a, the current crossing through the loop. What is the current crossing the loop? This is the only current, right, which is crossing the loop, which is equal to mu naught I. Can you see how we're doing this? So through this loop, if you see there's only one current which is coming out of this loop. This term is zero. This term is zero. This term is zero because all are at infinity. If you're at infinity, there is no magnetic field there. So that is the thing of taking this thing. So indirectly, what we proved, this integral B dx is nothing but n pi a square is B, that is nothing but mu naught into kt. This is your flux. Did you get the logic there? So I cannot find B, but I don't want B. What I want is integral B dx. So I want B into dx for this whole line. And because it is infinity, if I try to make a loop, the other three sides will be at infinite distance. If your wires are at infinite distance, what is the magnetic field due to the square loop at infinity? Zero. That means integral B dot dl for the other three wires will be zero. So whatever you get, integral B dot dl mu naught I, that must be only because of the solenoid. Flux आ गया, तो EMF will be d phi by dt. This is n into pi a square mu naught k. Current I is equal to E by R naught. Clear with this? That's how you can bring your Ampere's loop here. And the best thing about this question, right? This could be any shape, isn't it? This thing could have been a triangle. This could have been a circle. This could have been a hexagon. It should be a little symmetrical, isn't it? And should pass through the center. As long as you're sure the B is horizontal, passing through the center, you can take any shape and the answer will be same. Are you clear with the logic there? So that way it is. Infinite solenoid take is God. If you take an infinite solenoid, mu naught Ni, the current should pass through the solenoid, not through some outside square loop. Clear? The field inside the solenoid mu naught Ni, that I is the current in the solenoid. That's not the current from some other loop. Any doubts on this? So there, you can mix up Ampere's loop to get the flux like this. So that's one pretty good thing there. Right? Take a break. Come back by 9:40. We'll continue from here. Any doubts so far?
Sir, why is it necessary that it should pass through the
It
center?
won't be symmetrical, रे God. सोचो ना, B won't be horizontal then.
Yes, sir.
अगर B कैसा एंगल आ गया तो क्या करोगे?
Yes, sir.
B dot deal नहीं आएगा. Yeah. Others, any other doubts in the notes?
Sir,
Chalo, let's go ahead. Now let's see one concept here, combination of inductors. This is one thing. Now, normally when you have inductors, right, series, parallel, you can just directly add them up and, they behave like resistance. But if you have mutual inductance, it's a different ball game. So if you have series, so the first possibility, if you see, right, both the turnings are in the same orientation. They have same sense of rotation. So unlike resistors and capacitors, right, inductors, they interact with each other. So whatever field lines you're generating here, some of them will start entering this. So the fluxes will get actually enhanced. If this is L1 and this is L2, and this is mutual inductance, see how I'm writing the equation, huh? That is important. So if I write the equation, this is how I will write. So the flux in the first coil will be L1 I1, that is a flux due to yourself, plus mutual inductance M into I2. But here, because they are in series, I1 is equal to I2, so we get L1 plus M into I. You're getting it. So the EMF will be, so when you differentiate this, the back EMF, you will get it from there. Similarly, the flux 2 will be L2 I2. This is the flux due to your own self-inductance, plus mutual inductance M into I1. So mutual inductance is, the flux due to mutual inductance is due to the other current, right? The self-inductance is due to your own current. Again, same thing here. This will be L2 plus M into I. So the total flux on the system must be equal to L equivalent into I. So that would be L1 plus L2 plus 2M into I. So if you have mutual inductance and same sense of rotation, the mutual inductance is this, L1 plus L2 plus 2M. Suppose if you have in the opposite sense, देखो coil का turns reverse हो गया direction. So meaning when the current flows through this will generate a magnetic field in this direction. This will generate a magnetic field in this direction. So fields are fighting here. They're not supporting each other. In this case, L equivalent will be L1 plus L2 minus 2M. So depending on how you keep the coil ka orientation, the whole flux ka story will change here. Clear with this? So if you take M as 0, it won't matter. But if there is a mutual inductance, there will be an issue there. That is one. So series is pretty easy. Parallel, mostly if they ask you, it will become an advanced paragraph. Right? So now parallel, if you want them to support you, यहाँ पे देखो, situation will be a little different. The orientations will be reverse. Why? So when the current goes here, the field lines are going like this, so they're entering from the reverse. And I want this field to be up actually. So I want this to support. You're getting how it is? So if you want them to support each other, they should have opposite sense of rotation. Right? So anyway, so if you keep them in the same sense, they will fight with each other. So be careful with that. So if they keep in the same direction here, this field lines will try to enter like this. This field lines are also trying to enter like this. So the fluxes will cancel out. This is opposite sense, opposing. Anyway, that is the thing there. So what I want is for you to get me the equation. So if I give this opposite sense, okay? This is L1, this is L2, mutual inductance between them is M. So M will be generally given. Can you write the equations to find L equivalent? I'll just ask you that, find the L equivalent of this circuit with mutual inductance. Get me the equations. Solving is little lengthy, but can be done. But I'm more keen on you writing the equations. They both are in parallel. So Let this current be I1, let this current be I2. Okay. Now look at the voltages. Okay, how do you write the voltage in our inductor? L di by dt, but there is also mutual inductance. Okay, so the voltage across the V1 will be L1 di1 by dt. And if you're thinking, how am I getting this? Just get the flux and isko differentiate karo na, isn't it? If you differentiate flux, you'll get the EMF. So L1 di1 by dt, this is because of your own self-inductance plus mutual inductance di2 by dt. Is that making sense? So the flux will have two terms, L1 I1 plus M into I2. When you differentiate it, you'll get the EMF. This is your equation 1. Similarly, V2 will be L2 di2 by dt plus M di1 by dt. Now, because both are in parallel, V1 is equal to V2. And we also know current I is equal to I1 plus I2. So if you actually differentiate this, so now what you want to do, you want to replace this with one single inductor, L equivalent, the current is I, and you want to write this V is equal to L equivalent di by dt. Again, this V is same as V1, V2. So this V1, V2 is equal to V. This is your equation 3 and this is the other 4. So get capital I, substitute here, and you have to do something. You have to do plus and minus. You can play around, you'll get it. So this must be equal to V1, this must be equal to V2. So if you play around with this, you will end up with a result. L equivalent will be L1 L2 minus M square by L1 plus L2 minus 2M. You should try to solve and verify. Check it out for yourself once. This is when it is supporting. If it is opposing, बस denominator में plus आएगा. So opposing cases में this M का value, this will become minus signs here. Once you write the equations, physics part is over. Like after that, it all max का little complexity can be done. Just give it a try. I think it'll take 3-4 minutes. तो minimum तो जाएगा if you go full speed. I will leave it to you. But are you clear? So what I'm more keen is this equations. Did you get the equations right? Got it? Now I'll ask a question on this. So that'll be a little easier than these equations, but let's say how will you do this? Let's say we have a capacitor. We have a switch and we have an inductor. And we have one more inductor here. There is no resistor, nothing there. Okay, there's a mutual inductance. So generally they'll put something like this. So it's like a transformer kind of thing. They're interacting each other due to mutual inductance. Okay, this is L1, this is L2. This guy has a charge plus Q, this thing has a charge minus Q, this is C, and the switch is closed at T is equal to 0. Find the charge on the capacitor as function of time T. I can ask you a lot of questions. Find the maximum current in L2 and all that. Find charge on capacitor at time T. So this is like an LC oscillation, but with a mutual inductance. L2 be shorted. L2 में कुछ है ही नहीं. This gets shorted. L1 में there's only capacitor. So I don't think they'll ask you this parallel circuit and try to solve you because hey, thoda lamba, but something like this they're gonna ask you. So see, their perspective is not to make you solve a big equations. Do you know how to write when there's a mutual inductance and self-inductance? That is the main idea there. You know the story. Let charge Q flow from here after time t, and then current is I. So इसमें current I1 होगा, उसमें current I2 होगा. Get the equations and then try to solve. Let's see the equations. Once you got the equations, then it is fine. That can be done. So let charge Q flow from here. This guy will be Q minus Q. Let this current be I1. So this will be I1 and this would be some I2. You can take any direction, it doesn't matter. So now when you try to apply Kirchhoff's loop law here, you're going from negative to positive plate. Q minus Q by C minus L1 di1 by dt plus, maybe I will take I2 that way only. This will try to support and that will try to oppose. They're in the same sense, right? Opposite sense. Yeah, they're supporting actually. Because iska field length will enter here, that is supporting. So the direction is important. If the directions are messed up, signs will change. M di2 by dt. And also remember, I1 is equal to dq by dt. So my job is simple. If I can get di2 by dt in terms of di1 by dt, my job's done. Now, when you apply loop for this guy, minus L2 di2 by dt, the mutual inductance is supporting here M di1 by dt, and it is shorted, so you come back again to 0. That's what makes this thing easy. The equations will be easy to solve. So you got di2 by dt is simply M by L2 di1 by dt. We take this and substitute here. This will be Q minus C is equal to minus L1 minus M square by L2 di1 by dt is equal to 0. Differentiate on both sides. That would become minus I1 by C is equal to L1 minus M square by L2 d square I1 by dt. Obviously, this is an SHM, isn't it? There is no resistor, it's an LC oscillation. So you'll get I1 is equal to some I into sine omega t plus phi. How do you get I का value there? You can get it from charge. Actually, ना बिना differentiation भी करेंगे तो वो better है. You can write this thing as d square q by dt square. That would be better. Q minus of small q minus q by c is equal to L1 minus M square by L2. You can write this thing as d square q by dt square. Okay, better है. Q is equal to q naught sine omega t plus phi. At t is equal to 0, charge flowing is 0, and from there you can solve. Clear with this? So basically this q here is your q mean. Q minus q is equal to this, and from there you can solve it. It becomes an SHM. But are the equations clear, everyone? Equation 1, equation 2, equation 3. The reason this thing becomes easy is because you shorted this. If you just kept one resistor here, everything would go for a toss, meaning I1, I2 will get mixed up so badly, it becomes a little difficult to solve. Capacitor, you are going from negative to positive plate, potential rises. Any doubts on the equations, please check it out. Solving part, you can do it. The equations are the key. I'm expecting this some year. I don't know when it will come, but yeah. Because it's not difficult. Most people don't understand how to use that mutual inductance and self-inductance together. If these terms had been this way, this would become a minus sign. So it would change a bit, but yeah, it's still doable. It depends on that orientation. I told you, na? Are they in the same sense? So, aisa hai. If they're in the opposite sense, they will support. If they're in the same sense, they'll oppose. Same sense matlab rotation this way, they'll oppose. Right, so? Because iska field length aisa jayega, so ye turn karega na, so they'll try to enter here. But iska field lengths also they're coming down, so the field lengths are fighting there. So clear with this? So in case of series, same sense would support. In case of parallel, same sense will oppose. So this is one important model of question. So yeah, check it out. Got this? Now, if you have this capacitors coupled, right, you also have an energy then. So L1, L2, mutual inductance, let's say this is I1 and this is I2. So what is the energy of the system? So V1 is equal to L I1 d I1 by dt M d I2 by dt. V2 is equal to L d I2 by dt plus M d I1 by dt. So we know the total energy stored in the system is nothing but integral power into dt. And power is nothing but integral V1 I1 dt plus integral V2 I2 dt. When you integrate this, you end up with something like L1 I1 di1 plus integral L2 I2 di2 plus M I1 di2 plus M I2 di1. So this term will be half L1 I1 square plus half L2 I2 square plus M I1 I2. This will be the total energy stored in a circuit with mutual inductance. Where half Li1 square, Li1 square are what? These are interactional energies. These are the self energies, isn't it? These two are self energies, the energy stored in the inductor. So you know what is this? This guy is integral 1 by 2 mu naught B1 square dV. This is the magnetic field energy stored because of one inductor. What is this guy? 1 by 2 mu naught B2 square dV. What is Mi1 I2? This is the interactional energy. Some of the field lines which are going into the space, that is also energy. This is the interaction energy between the inductors. Basically, this is coming because of mutual inductance. And you know what is this? This is integral B1 bar dot B2 bar dV. वो formula याद है? I taught you this in electrostatics. Mu naught Mi1 I2. Anyway, just have a look at this, what we did. So I found the voltage, V into I1 is power, power into time is energy. If you just integrate this, you'll end up with this term here. That means if you have two inductors side by side with a mutual inductance, this is the total energy stored in the system. Half Li square is understandable, right? There is energy stored inside the capacitor inductor. But what is the energy stored because of the interaction, which is M into I1, I2? Clear with this? So this is the energy when you have two circuits together. If you think about this, you never had this kind of a problem with resistors and capacitors because resistors never interacted. If the current in one resistor is 20 and you bring it to another resistor, they didn't care about each other. Capacitors also never did that. Only these inductors have a problem. They start interacting, they induce fluxes and they start fighting. The inductors are anyway messed up. So if you actually think about this, this was the equation. So the energy total was integral 1 by 2 mu naught B square dV. This is 1 by 2 mu naught B1 bar plus B2 bar dV. So when you expand this, you will get 1 by 2 mu naught B1 square dV plus same thing here the electrostatics mein. B2 square dV, and the third term was actually the interactional energy. 2 times 1 by 2 mu naught B1 bar dot B2 bar dV. They can ask this question also. There are two inductors generating magnetic field B1 and B2. M is the mutual inductance. What is integral B1 B2 dV? So this term is your M I1 I2. This term is your half L2 I2 square. The self energies and the interaction energies. Is the idea clear, everyone? Now, based on this, they can make a paragraph on superconductors. This we did in the notes, but let me explain it again. And because these things are a little out of the portion, okay? So they will tell you something in a paragraph and they'll pop up things. Superconductors is definitely not there in the portion, but it's not difficult. They'll just give you paragraph, 10, 5 lines, they'll explain, and you're done. So we will also not go too deep into it. There's only one concept you need to know. Superconductors, right, have only one concept. No matter what you do, the flux remains constant. In superconductors, the magnetic flux remains constant. Means if you create the flux initially, after that, no matter what you do, the flux will remain constant. If you introduce some resistance and all that stuff, that's a different story though. So that is the current in the superconductors will change to keep the flux constant. That's it. We will not get too deep into it. It's a very simplified statement. A lot of things can happen. We will not get into all that stuff. At least for our level, this much is sufficient. To give an example, I told you this in the notes. Let's say we have a superconducting ring. And initially, let's say current was 0. Then what you did, you went and you brought a magnet and you kept it here. Now this magnet started generating field lines. So there is some flux. This is the flux due to magnet. The superconductor doesn't care. The superconductor will think, okay, my flux is phi because of the magnet. Now what you did, you went and you moved the magnet. Okay, you're not touching the superconductor. It is just there. Now, if your magnet is removed to infinity, now think about this logically. If you move the magnet, aren't you changing the flux in the superconductor? If you change the flux, won't there be a current in the superconductor? So the superconductor property is this. Now suddenly what will happen? The magnet is gone. This superconductor will induce a current I such that the same flux is equal to L into I. This is the same flux as this. And L is the self-inductance of the ring. So if you create a flux by a system and if you try to move that system, the new current which is induced in the superconductor will be such that the whatever is initial flux, you still have the same flux. Is the idea clear? That's it. This will be the concept. Mostly this they will explain you in like 5 to 7 lines and you're done. This is the whole idea there. So how they will frame a question on this? See. So we got a ring. We got a ring. So self-inductance cell, self-inductance cell. These are superconducting rings. They're very close to each other. So what is the meaning of that? If they're very close to each other, that means all the flux coming from one ring will pass through the other one. So indirectly it's telling you M is equal to L. That is the meaning of it. What is the meaning of mutual inductance? How much of my flux enters your system, isn't it? So if they keep them very close, all the field lines of one ring will enter the other ring. So M becomes equal to L. So their interaction is full. So this was I, this was I. So initially this was a system there. Now, if you separate the rings to infinity, how much work should you do? Find work done to separate the rings to infinity. Get this thing. It is the same question we did in the class notes. Like, I'm not even changing the numbers because hey, they can't really ask too much on this because it's not in the portion. So that is one thing. Whenever they try to ask you something completely new, they'll try to keep it simple. It is just they're trying to test you. Can you really understand what is your basic concepts and can you handle it? Again, what is the idea? The flux will not change. So first find the initial flux in the rings. And then argue with the statement, the final flux must be same. And then you'll get the final current. Work done by external force is nothing but change in energy. Let's go finish off. We will wrap up with this. I'm having a little headache actually. We will continue on Monday again. My eyes are burning for some reason. Let me check the AQI. Could be one of the reason. I might be blaming my eyes, but it could be pollution. No, it is better only. Last time it happened, I checked that it's 250 outside. So I just had to close my windows and everything, and it was fine. There we go. Let's see. So initially, what was the flux? So if you look at the flux on any one ring, the flux on any one coil is L into I1 plus M into I2. But luckily here, I1, I2 both are equal. M is equal to L, so this is 2Li. Now, when you separate them to infinity, so that guy is gone, the current becomes I dash. So the new flux must be still equal to Li. So this is L into I dash. So this is 2Li must be equal to Li dash. That means the current in the rings will double. This is the first idea there. 2Li square. That looks right, Prakriti, you got it. Is this idea clear? So initially flux was coming because of your own current and because of the other ring. But when you separated the other ring, you messed up the field, and because of that, the new current got generated in the ring. Now there is no interaction between them because they went to infinity. Is that clear? So the other ring won't interact because it is at infinity. Perfect. Now, what is the initial energy of the system? Now, this is where the coupled circuit will come. The initial energy will be half Li square, your own energy, half Li square, your own energy, plus M into I1, I2. This is the interaction between the two rings. Now, if you don't know that energy of a coupled circuit, you can't do this question. But M is also equal to L. So this will be 2 times Li square. Li square plus Li square, 2Li square. Clear with this? There is a second ring also, don't forget. Both the rings में current change हो गया. Now what is the final energy? Half L 2I whole square. The other ring also is half L 2I whole square. There will be no interaction energy. So there's only self energy is there. So this guy will be 4Li square. Therefore, the work done by external force is E final minus E initial. You gain that initial energy. So 2Li square. Is the idea clear, everyone? So when you took it to infinity to keep the flux constant, the current doubled. And then we found the initial energy and the final energy. Initially, there's an interaction. Finally, there is no interaction. So the difference must have come from somewhere. And since there's no resistance in the thing, so there could be no heat or anything. Yeah, so all that energy must have just stored in the conductors. So this is a pretty good thing because there are two different concepts here, the coupled circuits and the superconductors. Clear with this? And the coupled circuits, if you see, they have B1, B2 and everything. I want you guys to go through this parallel and series thing properly again. Try to do thing, go through the notes. We have it also in that detailed. Notes mein ye problem nahi hai. This was something new. The rest was there. So please go through that properly. Idea is important. And if you ask me, right, the best thing would be try to solve this question again on your own, get the steps and try to just see whether you're getting the result. That should help you. I just want you to be sure about how to write an equation when you have self-inductance and mutual inductance. Okay, there are a few more models. I make sure to go through the AMIGO notes. We have a lot more models. So Monday when we catch up, we'll continue. We'll wrap up a little early today. So I'll show you a few more important models of LR circuits, LC circuits, and then we'll do more AC circuits on Monday. ठीक है, with that we'll wrap up for the day, right? Anyone has any doubts in the class notes or anything, you can ask. But if you have more doubts, let's see it on Monday. So if you have any 1-2 doubts, you can stay back and ask. Or else, if you have more, let's see it on Monday. ठीक है, I'll see you guys on Monday at 6 o'clock. So any doubts, anything else, stay back, or else you're free to